Okay, this is the review for midterm number 3. It's probably useful for you to keep this relatively short and just direct you to a previous year's review, which goes through a summary of the concepts that have been covered in this portion of the class, which will be part of this midterm. So the material covered is the stuff from week 8, which is the energy equation, which comes from Reynolds transport theorem, but really we just use it in one dimension, both for mechanical energy and also for thermodynamic behavior as well. For dimensional analysis, Buckingham Pi and others from week 9, and pipe flow in weeks 10 and 11, but essentially we won't include pipe networks, and so we're not really including much of the material from week 11. So anyway. So the three questions, actually one of them repeats itself. The first one is on pipe flow and energy, so Bernoulli's equation with the pump involved and with major and minor losses. Dimensional analysis is historically always one of those, and again a repeat of not the same question, but the same material for the first one. And so the best way to pick up on this material is to go back to the video for midterm number 3 from last year, and look at the summarized concepts that are included in that, both from weeks 8, 9, 10, and 11, basically. Although I've already made the point that the material from week 11 is not there. So in terms of the concepts from those materials, so the three topics really are energy, dimensional analysis, and pipe flow. So for energy, you know that we have basically written Bernoulli's equation between an upstream and a downstream location. We have to write them upstream to downstream. We've included a pump in this, and along the way we have head losses in the system. And we know that we can write Bernoulli's equation as the upstream pressure, the upstream elevation head, the upstream velocity head, streamline velocity head, plus the pump head. And this has to be equal to the same components in the downstream locations. Plus whatever the head losses are. We know that the pump head is positive if it's a pump, negative if it's a turbine, but the pump head is merely the power in watts divided by gravity times the mass flow rate, which is functionally the same as the power divided by the unit weight of the fluid and the volumetric flow rate, because of course mass flow rate is just rho Q. And so just by making that substitution, you end up with those components. And the head losses we have are either minor or major, and those are given by a loss coefficient and the velocity head term. Or for pipe flow, it's something like a friction factor, length over diameter, and velocity squared over 2g. I guess important is that these are velocities within the pipe, not necessarily the upstream or the downstream velocities, which are defined here. And so that's something that's worth remembering. And that's pretty much it. There's also a thermodynamic equation. And you can see the form of that in the other notes, but I won't go through that here, so you can take that whatever you think it's worth. Okay. The second component is dimensional analysis. And the basic idea here is that if you can group the controlling parameters of a system into dimensionless groups, then you can examine the behavior of those groups individually and reduce the number of experiments you'd have to do and draw correlations between behaviors between a model and a prototype. And so the essential components of that are that we know some non-dimensional groups already. One is Reynolds number, which is velocity, length, density, and viscosity. The ratio of inertial to viscous forces. There's Euler number, which is a pressure divided by rho v squared, which is pressure force divided by inertial force. And the Froude number, which is equal to a velocity divided by gravitational force, where there's just a characteristic length that's included in some of these, and this is an inertial force to a gravity force in this particular system. We rely on Buckingham pi theory. To define the dimensionless groups that control our system. We know that the number of groups is equal to the number of variables defining our system minus the number of MLT, mass, length, and time components. So if mass, length, and time are all present, then this would be 3, and that would be the number that we subtract from the total number of variables, and that would give us the behavior of our system. Furthermore, we know that when we perform Buckingham pi theorem, which I won't do here, but we tend to use the repeating variables. They must include all of these mass, length, and time components that are present in the system. So they have to contain the parameters so that all of these parameters are included in the 3 repeating variables in the system. The 3 repeating variables that are chosen that are represented in this. The reality is that for an exam, you would be given the magnitudes of these because it makes marking it much easier for the graders. The other component in terms of dimensional analysis is its use is that we want to be able to analyze in terms of similitude, and that is that the pi groups for the model are equal to the pi magnitudes for the prototype, if you like. So that's true. And the similitude we want to ensure is that it is dimensional. So in other words, say length to diameter ratios of the two are equivalent to each other. That it is kinematically similar. And that is typically the Reynolds number is the same, so the flow regimes are identical. I guess this we sometimes have called this geometric, I guess. So in other words, all the scales, the length scales of the model are the same. So the model plane is exactly the same, looks exactly the same, but a different size than the real plane. And in terms of dynamic similitude, it typically means that the forces acting on the system are the same, and that's often recovered through the Euler number, which defines the magnitudes of the forces or the pressures acting on a system. So as long as we have that, then we can look at making sure that the pi groups for each of these components between the model and the prototype end up being the same. So that's that for dimensional analysis. And finally, for pipe flow, much of it is covered in this expression up here and in these two expressions here. But it's probably worth making a few comments. We talked about different types of problems. Type 1 is the easiest because you have you're given a velocity or a volumetric flow rate, and you want to calculate a pressure drop in the system, maybe, or the head losses in the system. And it's easiest because you don't have to iterate because you're given a magnitude of velocity. Type 2 systems, where we calculate a velocity, which isn't so straightforward because typically the head losses in a system vary with the velocity. And if you're not given an explicit magnitude of the head loss, you can't solve in one straight step to get it. But if you are given a head loss, then you typically can. And the third type of conditions are that you want to solve for the geometry of the system. And that's typically the most difficult because you have to iterate. Given a desired flow rate and a pressure drop, then you have to figure out exactly what the magnitudes of the pipes by making a first guess and then moving towards it. And so probably these latter two we wouldn't care too much about, but they would be closer to type 1 systems or some variants on those. We know that in looking at this expression for Bernoulli's expression, or the energy equation, when we have both pumps included and head losses included, both for bends and also for pipe flows. We know that for pipe flows we can get this from a Moody chart. We know the essential components of a Moody chart are that it gives us a friction factor. It's on a log scale versus log of Reynolds number. And there are two essential components to this. This kind of a laminar behavior, where this laminar behavior is that the friction factor is some function divided by Reynolds number, because it has a slope in log-log space. I guess this is log friction factor here. And that we have a boundary of behaviors here for smooth pipes, and that here we have a whole bunch of horizontal lines which represent different magnitudes of roughness coefficients. And so the essential components are this: in this turbulent regime, the friction factor equals constant with Reynolds number. So in one part it's a linear function, an inverse function of Reynolds number, and the other part it's constant with Reynolds number. So those define the two kinds of behaviors we have, and we can write basically the friction factor is, in terms of pi groups, a function of Reynolds number and roughness, relative roughness. So E is absolute roughness, D is the diameter of the pipe, and we can look at a number of equivalency formula to be able to define that behavior. So I think with that information, there's probably enough. There should be enough in these charts to be able to solve all the problems that we talked about. And so at least that gives you some compact look at what there is. And so again, the material is defined here. I don't necessarily need to go through the summary of concepts. If you look at the material for midterm number 3 in 2016, I think the YouTube video for that goes through these in much more detail if you want to just have a quick summary of what the individual concepts are that are used in these, the application, if you like, of these equations. Okay, good. All right, good luck. Thanks.